All right, well, it is 7 p.m. and good evening, everyone, and welcome to another virtual star party hosted by Vanderbilt Dyer Observatory. We are very happy to have everyone here this evening, and we've got a great lineup. We've got some new folks joining us, and so without further ado, let's just jump right into it. So I'm Dr. Billy Teets, and I'm the director of the Vanderbilt University Dyer Observatory. We are streaming live to YouTube, and we want you all to answer or to ask questions so that we can answer those live during the program. And if there's some that are posted in the chat that we can't get to, we're going to try to answer those through the chat as well. So it would be good if you can to log into the YouTube or into the YouTube channel so that you can answer or to ask your questions live on the program, and we'll be monitoring that as our presenters are presenting. So we'll do about a 10-12 minute segment, and then we will take a few minutes to do some Q&A, and then we'll move on to the next segment, and then finally we will wrap up with a final Q&A at the end of the program. And one final thing, I just want to thank my colleagues at Vanderbilt University who are behind the scenes tonight helping us out, including Brian Smokler of VU News and Communications, and my colleagues at the Vanderbilt Dyer Observatory, Helen Morissette, Nathan Griffin, and Alex Rockefeller. So our first presenter tonight is all the way up in Montreal, Quebec, Canada, at the McGill Space Institute. This is sorry, I lost my train of thought here. This is Mahesh Hareth, and he is a grad student at the McGill Space Institute, and he's going to be talking to us a little bit tonight about research with exoplanets. And so without further ado, Mahesh, if you wouldn't mind, go ahead and take it away.
Hello, everyone. Thank you very much for that introduction, Billy. So yeah, as he was saying, I'm Mahesh, and I'm a first-year PhD student at McGill University. And I'm actually studying something very specific called, well, if I put a label on it, it's called Exo Geoscience, which is essentially the conducting geophysics, but on planets far outside the solar system. And I'm pretty sure a lot of you who are joining in have at least come across the topic of exoplanets before in various forms of media. And it's from the mid-90s, it had essentially come far enough to be one of the most popular areas in astronomy in modern times. And initially, exoplanetary astronomy was all about discovering exoplanets. So the first exoplanet was found in 1995 called Pegasi 51b. Well, actually, that was the first confirmed exoplanet, but before that, they found another candidate exoplanet in 1992. But a lot of attention goes towards the one they found in 95 because it was confirmed as soon as it was found, called Pegasi 51b. It was a gaseous planet that was it was a gaseous planet that was actually was in orbit around a star in just 4 days. And right off the starting line, astronomers started to notice that exoplanets are quite unlike anything you have in our solar system, because for a long time, astronomers thought, especially planetary scientists thought, that when planets form, the gaseous planets are always going to form very far away from the star. But here we have a gaseous planet orbiting, practically touching the star in just 4 days. I mean, that's an orbital distance much closer than Mercury even, which takes 8 days to orbit our sun. Now, since then, a lot of work had been done with respect to finding new exoplanets, because the more you find, the more you can start building a picture on what these planets are like, what exoplanets are like. So after Pegasi 51b, they started finding more gaseous planets, a lot of them very close to the star. and then they started finding planets that are like Earth. When I say like Earth, what I mean is they're rocky planets. They are terrestrial exoplanets that are similar in mass and radius to Earth, but not necessarily identical to Earth. And then they started finding another class of planets called super Earths, which are planets that are more massive than Earth, but are still terrestrial in nature. And they also started finding a type of planet called sub-Neptunes, which are between the size of super Earths and Neptune sized planets. So they started coming across all these strange planets that you don't necessarily get in our own solar system. And this only increased for tenfold once the Kepler mission was launched and the Corot mission was launched. These were all in the late 2000s, and they started finding more and more planets. And per year, from what used to be 1 or 2 new planets found outside the solar system, they started finding hundreds. And very soon it's gone. It went from hundreds per year to, many hundreds several hundreds per year. And by now, more than 4,000 exoplanets have been confirmed so far. And with improving instrumentation, they're just going to keep finding more. And this is where things started to change, from finding exoplanets to actually learning more about the nature of exoplanets. For example, what are their atmospheres like? What are their interiors like? Can they be habitable? Can they host conditions that are very similar to what we get on Earth or any other planets in the solar system? Can they have things like tectonic plate activity? So many different things that we see in our own solar system, we try to attribute, see if we can detect those things in those planets over there. This is where things actually get interesting, because now things like atmospheres you can observe, but interiors, that's something that we can't actually observe directly. I'm going to start sharing my screen so that I can start the main body of my, oh, hold on. Sorry, wait. Wait. Okay, there we go. I'm just going to start the presentation there. Oh, sorry. There we go. Okay. Everybody can see this, right? Okay, great. Now, geoscience outside the solar system, it's a tough thing to do. Even, I mean, it's tough enough doing geoscience in our own planet, on Earth, mainly because it's very difficult to actually see what's happening down hundreds of meters below the surface. I mean, we've only like humans have made maybe, I don't know, 1 kilometer or 2 kilometers below the surface at most in terms of penetration. So most of what we know about the interior of the Earth come from things like seismic activity and by observing our own Earth's magnetic field. Now, similar things can actually be used for learning about the interiors of extrasolar planets. In this case, as you can see from the title, geoscience, Exo Geoscience, as we call it, beyond the solar system. And and much like now, the reason why I'm concentrating on terrestrial planets is mainly because terrestrial planets are the ones that are most likely in terms of places where to find habitable conditions and hopefully life even. So those are the kind of planets that I concentrate on with my research, trying to learn more about what's happening inside these planets. Now, if you're wondering why study these interiors, right? The interior actually determines so many factors about how a planet behaves, for example, things like convection, right? Convection in a planet's interior determines how things like plate tectonics work, tectonic activity works, and how materials can get recycled from deep inside the planet up into the surface, and whether things like you can have things like outgassing happening in planets, because if you have a dynamic interior where you have lots of material getting recycled and gases being released, then that means it's more likely that you could have an atmosphere that keeps changing over time. Because Earth's atmosphere, even though it started out as hydrogen and helium, an atmosphere of hydrogen and helium way in the past, 4.5 billion years ago, that hydrogen helium atmosphere slowly evaporated away over time, only to be replaced by nitrogen, oxygen, and carbon dioxide, all of which started getting released from deep inside the Earth's interior. For those things to happen, you need a dynamic interior. And to know whether or not there's a dynamic interior going on, we need to understand we need to study the interior structures of planets. Now, I'm sure a lot of you, well, at least some of you have seen this particular schematic of what the interior of a terrestrial planet looks like. This is what the interior of Earth is supposed to look like. You have an inner core, which is supposed to be solid iron under extreme pressure. And just outside the inner core, you have the outer core, which is liquid iron. So you have a solid iron inner core and a liquid iron outer core. So this is more or less made out of, all made out of iron. Now, afterwards, you get to the, afterwards you get to the mantle, which is essentially made out of a whole mixture of elements. If we take Earth, for example, it's made out of magnesium, silicon, oxygen, more iron, calcium, aluminium, sodium, vanadium, and whatnot. And you get the occasional bits of uranium and platinum and all that. And then you have the crust, which is essentially the part that we live on. It's a solid layer, while the mantle kind of alternates between liquid and solid, and you get things like solid state convection going on. Ultimately, you get to the crust, which is pretty much solid, and you get conductivity, heat conduction happening in it, and we sit on top of the crust of any, and this is where you get things like mountains and all that happening. Now, the one thing, so that's a brief overview of what the actual structure of a planet looks like. But why this is important is down to the fact that you actually get the structure enables what we call a geodynamo. Now, we get a geodynamo going on when there's convection happening between the inner core and the outer core. So the combination of thermal convection happening and materials that are getting released from the inner core to the outer core, combined with the rotation of the planet, generates electrical currents in the outer core, in the liquid outer core. And this leads to what we call a geodynamo. And this geodynamo is actually what generates the magnetic field of a planet. And the magnetic field of a planet is actually extremely important. I can't stress how important a magnetic field is. Without Earth's magnetic field, we would not have protection against harmful solar radiation. Our atmosphere would be, well, essentially it would erode away over time without our magnetic field, because the solar wind and cosmic radiation just bombards the planets with extreme malice, and it's going to start eroding materials away over time slowly. And if we didn't have the magnetic field over over 1 billion or maybe 2 billion years, our atmosphere would be gone. And I don't have to stress how important an atmosphere is for life to thrive. And that's what I do when I do study Exo Geoscience. I try to look at how other planets, what conditions are necessary for other planets to have this kind of geodynamo going on. And one of the reasons why it's interesting to explore what happens in exoplanets, in the interiors of exoplanets, is because a lot of these planets are very different from what we get here on Earth, not just in composition, but even in things like mass and radius. How would the mass affect what's happening inside the planet? And would it be drastically different from what you get on Earth, or would it be very similar? That's something I'm looking at. Specifically, a type of planet known as super Earths have been found in abundance all over the galaxy. For example, Proxima Centauri actually hosts a planet which is 1.2 Earth mass, and it's essentially an Earth-type planet. But there have been many other planets found in other star systems which are in their habitable zones that are more massive, like, for example, 1.3 Earth mass, 1.4 Earth mass, essentially planets that could potentially be conducive to life. And what I do is I actually do research to find out whether this can happen. So what I do is I actually simulate the interiors of these kinds of planets, these different planets that are far, far different from what we get here on Earth. So I look at things like optimal conditions, what conditions enable a geodynamo to happen, what conditions are actually good for a stable atmosphere and for stable magnetic field, and whether you get activity happening inside the planet that is strong enough to generate things like thermal currents and plate tectonics to happen. And this is actually just some figures I've made, some pretty pictures I've made of what the insides of certain kinds of planets look like. So you can see one of the planets over here, right at the top left, it's Proxima Centauri b, which is the closest exoplanet to our solar system. So what this CMF is something called the core mass fraction. That is how much of the mass of the planet is concentrated in the core. Now, the core mass fraction is actually highly dependent on how the dynamics of the interior work. So this is one. So the core mass fraction in Earth's interior is 32%, in case you're wondering. Proxima Centauri b, according to my research, probably have something that's 39% core mass fraction. So the core is slightly more massive than what you get on Earth. Kepler 186b is another planet that is supposed to be Earth-like and supposedly in the habitable zone of its star, Kepler 186. And from what I have found, the core in that planet is only 24%, which is practically similar to the moon. And then we have another planet called Ross 128b, which is actually, again, a star that is very close to our solar system and has a planet that's very much like Earth in the habitable zone. And even though it has the same mass, according to my research, it's very likely that its core is actually much, much more massive. We have like something as high as 52% in its core mass fraction. So these are just some work I've done. And what I do when I look at modeling is I look at things like convection and thermal dynamics in the planet's interior. This is a schematic of how thermal convection happens between the core and the crust. And this is what drives activities such as the movement of plate tectonics in planets, which is very important for atmospheres to come about. And yeah, another thing I'm looking at on how to model these planets is looking at what kind of materials are inside these planets. For example, how much oxygen there is, how much silicon there is, how much aluminum there is, magnesium. All these things are very important in determining what kind of interior activity is happening, and in turn, how they affect things like atmosphere production and magnetic field generation, all of which are very important for habitability in planets. And I don't know if anybody would be interested in this, but this is just some simulated results of what their magnetic fields are like. I'll just tell you what these means. They essentially say most exoplanets that are larger than Earth have magnetic fields that are much stronger than that of the Earth, most of the time, not always. But why did that get shut? Oh, never mind. But yeah, so that actually was my last slide. And that should give you an overview of the kind of research I do here in McGill and the kind of work we are doing overall related to exoplanets. But there are so many other things to talk about in relation to exoplanets, and I would be more than happy to discuss anything related to exoplanets, not just exoplanet interiors, even atmospheres, detection, anything. So yeah, thank you so much for listening to my talk.
All right. Well, thank you very much, Mahesh. We do have a couple of questions that came through. Are there any confirmed exoplanets that are tidally locked?
Confirmed ones. So terrestrial planets, I would say no. As far as I'm aware, there aren't any confirmed tidally locked exoplanets, tidally locked terrestrial exoplanets. But there are tidally locked gaseous exoplanets that had been found. So yes, there are tidally locked gaseous exoplanets. But if a planet is close enough to a star, I would say it's very likely they're tidally locked anyway. But to confirm it, you would have to do much more. You would have to do more observations to confirm whether they're actually tidally locked.
And for everyone at home and for us as well, would you mind explaining what tidally locked means?
Yeah. So take our moon, for example. What you mean by tidal locking is when the rotation rate of a planet is equal to the orbital period of a planet. So if we take Earth, for example, the Earth takes 24 hours to spin on its own axis, but it takes 365 days for it to go around the sun. If by any chance our rotation rate, rather than 24 hours, turns out to be 365 days also, right? If it takes 365 days to revolve around itself, and it takes 365 days to go around the sun, that would mean the Earth is tidally locked. You get that with the moon, actually. The reason why we see only one phase of the moon is because its rotation period is equal to its orbital period. So that's what tidally locked essentially means, that only one side of the planet faces the star. It doesn't mean the planet's not spinning. It's just spinning at a rate equal to its orbital period. And this is something that is very likely to happen when a planet is very close to the star, because the gravitational tug of the star starts slowing down the rate at which it spins. So if it's close enough and the tidal effects are strong enough, a lot of planets could easily end up getting tidally locked. So yeah, that's what tidal locking is, for those who are unfamiliar with that particular term.
In fact, our own planet Mercury is pretty close to getting to a tidal lock. Is that correct?
Yeah, that's correct. It's actually in something called 1-3. Is it 3-1? 1-3? Doesn't matter. 1-3 resonance. Essentially, it takes 3 times as long for it to spin on its own axis as it does to go around. Oh no, sorry. It takes 59 days for it to spin on its own axis. And when it rotates 3 times around itself, it makes 2 orbits around the sun. So okay. Yeah, so that's what you call 3. Oh yeah, there we go. 3-2 resonance. Yeah.
Gotcha.
Yeah.
Are there any non-metal elements found in the mantle of these exoplanets, or even Earth?
Non-metal elements. Mm-hmm. Yeah, there's silicon. Okay. So there's silicon. I would say silicon is highly abundant. I would say it's very likely silicon is highly abundant in most terrestrial planets. And of course, there's calcium. Okay. Apart from that, sodium. Sodium. You get sodium. You get silicon. You get phosphorus. You get calcium. I would say those are the most abundant non-metal ones I can think of. You can get things like oxygen and of course carbon, but they would be combined with other elements. Yeah.
Okay.
Yeah.
And one more question for you. Any ideas how a stronger magnetic field could affect the evolution of life on one of these planets?
I would say it's very likely that it would be good. It would provide very good protection against stellar radiation and stellar winds. So if they have an atmosphere, they would be very well protected, I would say. As for a direct effect, I would say that would have to have much to do with what kind of life would be there. I mean, say for example, you have birds in a place like that.
Mm-hmm.
they would have to evolve in I guess, different adaptations to deal with a stronger magnetic field.
Gotcha.
Yeah.
Okay.
Yeah.
Actually, I said we had one more question, but here's one more question. Do you have both a geology degree and an astronomy or physics degree?
I don't have a geology degree. I actually have a physics degree.
Okay.
Yeah, and yeah, that's about it really. My background is mainly in physics and on certain aspects of space systems design. That's about it. But I got into this. Most of the geoscience aspects I self-learned in the last few years. Yeah.
All right. Well, thank you so much. That was a
You're welcome.
fantastic presentation. I learned a lot, and I think everybody else at home did as well. So thank you very much.
Thank you very much.
All righty. So folks, if you have more questions that pop into your head as you're mulling over what we've just heard, then be sure to post those in the chat. We're going to keep track of those and try to get to some more questions at the end. But now we're going to come back down into Tennessee, and we're going to go over into East Tennessee and join Adam Thans, who is with the Bays Mountain Park and Planetarium. He is going to talk to us a little bit about one of my favorite constellations and some of the cultural ties in to that. So Adam, take it away.
Thank you, Billy. Well, thank you for having me here and sharing the night sky virtually, but really just really sharing our love of the night sky with everybody. And so I'm going to be talking about the constellation of Orion and how the Greeks and also the Inupiaq saw the same exact stars. But first, I'd like to point out, how can you find it? Where can you see it in the sky? Because I know some others are going to be discussing objects in the constellation of Orion, celestial objects after me. So I thought I would at least do a quickie introduction on that. And of course, got to have a prop. And so right here, I've got something very basic that really everybody should have. And I know that the Vanderbilt Observatory through Billy and their team, that they have a planosphere like this that you can print and make your own at home. And so, it's low tech, but hey, it still works great. And it's actually the best way to learn about the night sky. So what is it? First of all, planosphere, as you can see, there's the center wheel that rotates. And you probably notice that there's some dates and times. You basically line up the date, your current date, with the time of night, okay? And you can see where it's early February, around 9:30 is how it's set, which is, how do I do this backwards? Right there, about 9:30, early February. So that means, this sky is what you see. And here's what you see off to the east and off to the west, and of course the north and the south. And so you just rotate the chart about based on how you're pointed. And I'm going to bring this in. I hope you can see it. Right there is Orion. And so it's basically in the southeast sky right now after sunset. It looks like an hourglass shape. It is very prominent. It's made with very bright stars. So there's my prop. And now I'm going to show you a nice picture of that part of the sky. As you can see, right dead center, I've got the constellation of Orion. You'll see what looks like a small hourglass shape. You'll see 4 stars in a rectangle and 3 stars at an angle right in the middle. So looking at the 4 stars that make the rectangle on the, well, I don't know, you don't see my arrow, that's okay. But you'll see an orangey type star, a red-orange star there. That is Betelgeuse, which is a red supergiant star, which recently had some very interesting variation in how it looked. This was about a year ago now. And it turns out that it was dusty material orbiting the star that was just kind of getting in the way and lowering the brightness of the star a little bit as far as how we see it. So kind of like, I don't want to, it's not, I'll say space fog, but it's not a fog. Space debris that's just getting in the way and dimming the view. And then diagonally down to the bottom right is Rigel, which is a hot blue-white supergiant star. And in the middle is the belt of Orion, and those 3 stars right there. And then kind of hanging from the belt in the center there, you'll see 3 stars very close together, going straight up and down. Excuse me, that's the Sword of Orion, which includes the Great Orion Nebula, which will be, as I understand, talked about a little later tonight. Yes, that's right. They're following me. So you're going to be learning about the Orion Nebula. It's in the Sword of Orion. To how I see it, you should be seeing to your upper right a V shape of stars with a bright star that is red in color. That is the face of Taurus the Bull, with the nose and the 2 eyes at the ends of the V. And if you notice the belt stars, they point to the V shape. So you can find the face of Taurus the Bull. If you continue with the 3 stars, the belt stars, go past the face of Taurus, you'll find a little cluster of stars that are called the Pleiades. So these are all very easy objects to see if it's even halfway clear in the sky. You can see these objects. And then if you follow the belt stars down to your lower left, you're going to find the brightest star in the entire night sky called Sirius, but it's spelled Sirius. So what I'd like to do is bring up this picture. Now I'm going to go back and forth a little bit. Here's how it looks in the night sky. Here's what the constellation pictures on top of it. You can see the shoulder stars of Orion, the belt, the sword, the knees, and then you see the face of Taurus the Bull and the Pleiades on the back of the bull. And then to the other way, with the belt stars, you find Sirius, the brightest star in the night sky, as like the collar or neck of the big dog. And of course, if there's a big dog, there is a little dog too. And so those are the hunting companions of Orion. Now, this is the classic Greek view of the night sky. If you do some research on your own on Orion, you're going to end up finding all sorts of stories about Orion and various ways in which people looked at these stars from different cultures, and even in the same cultures, but from different eras, hundreds of years BCE to 1,000 years ago, 500 years ago. It keeps changing based on the culture of the time, even in the same physical place on Earth. And so things do change. It is considered possible that Orion may have been a version of Hercules, and that one of the tasks of Hercules was to fight a bull. And so there's this kind of strange mixture of different stories and how people saw it in the sky. So I'm going to share 2 stories with you. I'm not the best storyteller in the world, but I'll try my best. We're going to start with the Greek story of Orion, which are the cast of characters are right in front of you. And again, if you go out in your night sky, tomorrow night should be clear, and it'll be cold, but you can even see them through a window. Turn off the lights in your house. You can look through a window. It doesn't even matter if it's cold out. You can see it. Look to the southeast sky, and you're going to see Orion rising. So this story, I'm going to be using the text from Ian Ridpath's Star Tales, which is online. You can actually find his book online and his stories. But this is kind of a common view of a basic story of Orion. So according to myth, Orion was the son of Poseidon, who was the sea god, and Euryale, daughter of King Minos of Crete. Poseidon gave Orion the power to walk on water. Homer, in the Odyssey, describes Orion as a giant hunter, armed with an unbreakable club of solid bronze And you can see him holding it with his right hand over his head. In the sky, the hunter's dogs, which is the big and little dogs, which you see there, their proper name is Canis Major and Canis Minor. I think you can figure out that major and minor mean big and little. Canis, like canine, means dog. So Canis Major, big dog, Canis Minor, little dog. Follow at his heels. In pursuit of the hare, which is the constellation Lepus, the hare. It's actually right underneath him. I don't have it highlighted in this picture, but if you look under his feet, like literally just under his feet, you're going to find 6 stars, 6 or 7 stars there that are somewhat bright. Those make Lepus the hare. And again, this is right underneath Orion. So the story, one of the Greek stories goes, on the island of Chios, Orion wooed Merope, daughter of King Enopion. I'm going to pause here for a second because Merope is one of the 7 sisters, also known as the Pleiades. Do you remember where I talked about that and where it is in the sky? Give you a moment, a little thinking time. I think you remember, if you follow the belt stars of Orion, you go up to the right, you go past the face of Taurus the Bull, and you find that little cluster of stars. Some people confuse that with the Little Dipper. It's not the Little Dipper, it's the Pleiades star cluster, or also known as the 7 sisters, and they each have a name. One of them is Merope. So, Merope, daughter of King Enopion, apparently without much success, for one night while he was wooing Merope and without much success, for one night while fortified with wine, he tried to take advantage of her. In his punishment, King Enopion put out Orion's eyes and banished him from the island. It's a pretty severe punishment, but I guess well deserved. Orion headed north to the island of Lemnos, where Hephaestus had his forge. Hephaestus took pity on the blind Orion and offered one of his assistants, I'm going to mess this name up, Sedalion, to act as his eyes. It's basically an aid to help him walk around. Hoisting the youth on his shoulders, Orion headed east towards the sunrise, which an oracle had told him would restore his sight. As the sun's healing rays fell on his sightless eyes at dawn, Orion's vision was miraculously restored. The story does continue on. It's actually quite a long story, but it kind of gives you a flavor of the mythology and the mystery of, these characters and the night sky and how they related to the night sky, how they related to people on Earth, related to the sky. So I didn't mention earlier, but I will mention now that the night sky was the first storybook. Even just a few hundred years ago, almost nobody had written books like they physically owned. That was an extreme luxury and very rare. The night sky was the one way in which all cultures could use as a storybook to teach lessons to their young ones and to pass those stories on to travelers. Usually these were people who bartered and were like traveling salesmen, so to speak. And these trade routes then shared these stories amongst different cultures. So the night sky, very important to all of us. Think about what could you do at night? You had an oil lamp, you might do a little bit of something maybe, but the night, everybody had a hopefully clear, but a dark night sky, even in the middle of any kind of large, I'll call it a city, but essentially a place of a lot of people, but there's no lights. So everybody had the stars. The next story I'm going to share is very different. And it's especially because of where the culture was. So the Greeks, they were in they're in the area around Europe, but closer, more southern, and surrounded by water. Their life was very different than this other culture. It's very lush environments. We're in Greece, so you can see how Orion is dressed. Let's go to the next story. Take a moment, notice the characters and how they're dressed. So you can see who they are or who they are not. They're not basking in the sun by the Aegean Sea. They've got thick winter parkas on. And our previous speaker, Haresh, they just said that they had a foot of snow yesterday and today. So these people are actually much farther north. They are the Inupiaq. The Inupiaq is like a subsection, a part of a larger group of people called the Inuit. The Inuit is the proper term instead of using Eskimo. Their term for themselves is the Inuit, and they still exist. They live up north. They're in the Arctic Circle, way north Canada. These are indigenous peoples who live in these extreme environments. Part of the Inuit is the Inupiaq. So this story comes from them. And it's the story of Nanook. There is a famous movie called Nanook of the North and a book of it as well. And this is what, this story is from that legend. And just thinking about where that is, physically, it's not going to be warm and nice and toasty and walk around in just, shorts. You've got to have all these winter clothing on. So there's ice and snow almost all the time. You also see another character there that is only found in the Arctic Circle, a polar bear. So it's a very, very different kind of place. And you can notice that we're zoomed in on the stars of Orion. But now for the story of from the Inupiaq of Nanook. And very briefly, there is this polar bear called Nanook. And the story goes where she was out hunting for food for her cubs. And at one point, these 5 wolves basically were surrounding her and attacking her. And things weren't looking very good in the situation until the 3 hunters that you see in the center there, which are in the belt stars of Orion, the 3 hunters chased away those wolves, saving Nanook. And so to honor this brave action, these characters were placed in the sky for all to see and learn from. Notice the difference in how the Inupiaq saw these pictures in the sky compared to the Greeks, or really almost all other cultures and their constellations. These are single stars for each character, as opposed to a whole bunch of stars making a dot-to-dot picture for one character. So the 3 belt stars of Orion are the 3 hunters. Aldebaran, the fierce red eye of the bull, which is at the end of the V, at one end of the V of the face of Taurus, the bull, is Nanook. The other 5 bright stars of the face of Taurus, the bull, make the 5 wolves. And you can see the Pleiades off in the upper right. But this is a very different way of seeing the same exact stars. And it's very, it's pretty neat that there's this change of even perspective of how they even looked at the sky. And of course, I find it very unlikely that anybody from the Greek culture from ancient times ever came in contact with anybody from the Arctic Circle. But it would have been very interesting that they would have been trading their stories and sharing with each other their culture's views of the same stars. That's pretty much what I have. I will go back to that, just the night sky view. So again, we have Orion the Hunter and his two companion dogs, and Taurus the Bull, and the Pleiades, or of course the three stars for the hunters, and Nanook being the red star Aldebaran. And if you have any questions, I'd be happy to answer. And I hope you enjoyed the stories. The real fun, go outside and enjoy the real night sky, and you don't even need any equipment to do so.
All right. Well, thank you very much, Adam. Those are really interesting stories. I always love hearing about the mythologies, especially of different cultures I'm not familiar with. So,
Billy?
Still can't hear me? No? Can anybody else on the call hear me?
I can hear you. I can hear you, Billy.
Yes, we can hear you.
Oh. It's me. Hang
Okay.
on. Why does this not work? Come on. Okay.
All right. Can you hear me now?
Yes, that was my fault. My speakers turned off by.
Don't worry, I do that all the time. So, no, I was just saying, thank you. That was really interesting tales, and I always love learning about the mythologies, especially from different cultures that I'm not familiar with. I had a couple of questions. I was wondering if you had any recommendations for maybe some books about the mythologies of the constellations, whether it's Greek or Inuit or.
Well, I don't know specifics of too many books. Since I read from this, I will give a plug to Ian Ridpath's Star Tales. It is online. All the stories are there. He is an astronomer and planetarian person. I'm pretty sure he is. If you really like the scholarly view of the night sky, and I mean it, I mean scholarly, then you are going to want to find, let's see, here we go, Star Names and Their Meanings by Richard Hinckley Allen. This, you can find it as a scan online. It's kind of a rough scan. The book does exist. It was one of those Dover publications that are so great. And that was written in 1899. It is a compilation of all sorts of cultural views of everything in the night sky. And if you don't know about this, you really need to kind of scan through it, look through it. It has, you name it, Greek, Arabic. It has various eras of Greek and Arabic understanding and viewpoints of the night sky, constellations, and also stars, their names, their meanings, how people saw them, Chinese cultures. It goes on and on and on, and then even to like the modern view of 1899. But it is a very interesting book, and so it has the pronunciations for the stars. It also actually writes them out in Greek. If it is a Greek word, they're in Greek. So I've always found that to be a really interesting story. Just kind of looking up at my books here, a good book to learn about the night sky in general, which has all sorts of star lore, but also about objects in the night sky, is 365 Starry Nights. It's kind of a classic book from Chet Ramo. Actually have it right here. I don't knock things over. Okay, right there. Whoops. 365 Starry Nights from Chet Ramo. Yeah, a lot of people are, and it breaks down the night sky into singular days. So it's kind of like, it's not a calendar, but it's going to talk about something that is visible on that day in the night sky. Sometimes it's a constellation. Sometimes it's something detailed within it. It could, here I'm looking at using the night sky for navigation. So it's a whole collection of just interesting, I wouldn't say stories, but it's just the lore of the night sky, but also the science lore. I'll put it that way. And so I'm sure this is still in print. It's a neat book. There's lots of others. Really, and online you can find just about anything, and you're going to find all these different variants of that. Orion itself is many pages in the Hinckley Allen book, and it goes on and on about how different cultures saw and even understood the constellation of Orion, but from different cultures, and how the spelling came about and where the star name came from. I'm talking to myself. I'll pause there if you have another question or if somebody else has a question.
No, that's great. And I always, it's always fascinating to read what the star names actually are supposed to mean and where that actually comes from. A lot of them are really surprising. So, yeah. And if you wouldn't mind, someone asked if when you get time, if you could put the titles of those books in the chat.
Yeah.
Okay.
Yeah. And then you'll, I guess, post it or something, or.
Yeah, I'm logged into YouTube. So yeah, if you can put it in the Zoom chat, I'll transfer it over during our next presentation. All right, well, thank you so much.
Sure.
So our next speaker is Jeremy Veldman from the Memphis Astronomical Society, and he's got a couple of his colleagues from the society with him tonight. So I'm going to go ahead and turn it over to him so that he can introduce us to everyone. So Jeremy.
Thank you, Billy. It's nice to have the band back together. It's been about a year since we've done one of these, so it's great to be back and doing these again. Can you hear me all right? Somebody give me the thumbs up.
Yeah, I can hear you.
Excellent. Okay, so getting back to Orion, let me just share my screen here. So again, if you look in the southeast eastern sky, you will see Orion rising right after sunset. And this is a great time of year to be viewing this constellation. And it gets higher as the night goes on. About midnight, you'll see it very high in the sky. And you can actually see the chart here of Orion and all of the stars. And you can also see a snapshot of Orion taken by yours truly about a month ago. And what makes Orion so fascinating from an astrophysics standpoint is you're really seeing the full gamut of stellar evolution. So you're seeing the life and death of stars. I mean, you see the bright star Rigel in the lower right here, which is one of the knees. Again, that's a blue supergiant star. It's moved off of main sequence. Our sun and 85% of the stars in the universe are what called main sequence stars. I'll spare you the details, but they're basically going through their ordinary stages of nuclear fusion. When they get older and they move off of main sequence, they become giant stars and eventually near the end of their lives. So that's what Rigel represents, is the blue supergiant star. And then also, of course, we have Betelgeuse in the upper left here. That is a red supergiant star and very large. I mean, 5 astronomical units in diameter. If you took it and plopped it down in our solar system, Jupiter and its orbit would essentially fit inside of the star. It's just absolutely enormous. On the other end of the spectrum, you have the dawn, the beginning of the birth of stars. And that's what we're going to show you tonight. It's the Great Orion Nebula, M42. M stands for Messier, object number 42. Right around the time of George Washington, there was a person named Charles Messier who set out to become world famous for finding comets. And he found a whole bunch of things that weren't comets and cataloged them into what we now know to be a catalog of 110 deep sky objects. And that's how you learn the night sky when you're getting started. If you go through all 110 and you find them, you will become a competent, basically backyard amateur astronomer. So Charles Messier essentially became the poster child for astronomical ineptitude, and in so doing, gave us a catalog that really helps us learn the night sky. So M42 is the Great Orion Nebula, and you can see it's located right here in the sword. And it appears as a very faint, fuzzy smudge in the constellation of Orion. It's a great binocular target, and it's absolutely spectacular when you look at it through the eyepiece of a telescope. Now, tonight, I've got 2 of my colleagues on who are going to show this object. And to do it, they're going to use a telescope that they've recently picked up called Stellina. And I've got Mr. Rick Honey and I've got Mr. Merrill Miller online. And I'm just going to turn it over to these gentlemen to introduce you to Stellina and show you this object. Rick, are you there?
Yes, we're here, and you should see an image of Merrill Miller
Come out and see Stellina.
and at the telescope, which is a small robot-looking thing sitting on the ground there.
Well, we've been looking for a way to take our outreach to a new level. And as Rick said, as Jeremy said, that we acquired this Stellina, which is basically a robotic telescope. And it's got a 400 millimeter focal length telescope with 80 millimeter lens. It's got some neat features of it's got a built-in Wi-Fi that can broadcast to up to 10 devices. It's got a 6.2 megapixel camera that it can take pictures real time. It's got its own dew heater if it needs to have that. And it basically tracks, it's an alt-as telescope that tracks as we rotate the Earth. Now, we set this up about 45 minutes ago when it was quite a bit warmer than it is now. And so we were waiting for you guys to get done. We got a little heater on it. Actually, the ambient that it operates on is 0 degrees is the minimum. Fortunately, we have a little quartz heater, and it's doing a good job keeping it warmed up. We've got it now set towards M42, as Jeremy was speaking about. And the thing that's really cool, we take the next level, and Rick's going to show you that, is how we're going to broadcast it to larger crowds. So, Rick, you want to show him what you got there on the screen?
All right. So what I've been trying to do personally for a long time is be able to set up at a star party and have people see what telescopes are looking at without them, especially with things like Boy Scouts and what have you, having to stand in line to get a look through an eyepiece. And so now we're set up to have a monitor available that will be connected to, let me share a screen. And this is where, okay. And we launched the Stellina app, and we tell it to go to M42 Orion. And what you should be seeing is a screen, is the Stellina app screen that everybody will see.
Well, this is the about here. Yeah, I think you're at the go to. Did you get it? It says about.
Is it not going?
I think you need to go.
I told it to observe.
Okay.
Okay, I'm sorry. Now it's
There you go.
making its way over to find the M42, the nebula. What Merrill didn't talk much about is you basically set this thing on the ground, turn it on, and come back in 10 minutes. And it knows exactly where it's at, exactly what it's pointed at. It does plate solving, or basically constellation recognition. It takes a quick picture of the stars and then compares it to a catalog to say, this is what I'm looking at.
It also has autofocus too. I forgot to mention.
It does have autofocus, and it throws up cute little tidbits of knowledge for you to think about while it goes and grabs its first image. That'll give us a second. And this is a live demonstration of exactly how long it takes for this to work and how long it takes to actually produce a usable image. This thing will do image stacking so that once you take that first image in a few seconds, as you sit there and watch the image, this is the fun part.
Yeah, it's starting to
It's collecting photons. and it'll stack these images and improve the resolution as you just sit here and watch it.
I think it takes 10-second images and then stacks them.
Yeah.
It's running particularly slow because it's cold.
It's about 27 degrees out here. So
It's cold.
okay, here it goes.
There we go.
All right. That's the first 10-second image. And that is honestly just incredible. And this will continue to get better as you stay on it. Can y'all hear us?
Yep, we can hear you. Yep, we can hear you.
Okay, I thought I lost audio there for a second. So this is M42, the Great Nebula in Orion. And this was just that easy. And what we have here, stop broadcasting. Well, yeah, I can't stop broadcasting and still show you, but that picture was showing on that screen just a second ago. And so this works out really well in a crowd. We were at Memphis Pink Palace Museum, or the museum formerly known as the Pink Palace. Now it's called Memphis.
It's called the Mosh Pit, the Memphis, what is it? Museum of Science and History.
Yeah, Mosh. Good
Terrible
God,
name.
it's awful.
One thing you might want is it has the catalog to built into it. The catalog built into the.
Oh yeah. So this has got a catalog of some. I don't know how many objects. Let me share screen again. Go back to that real quick. Sorry, my fingers have gotten cold and it's hard to drive. So this, their software that drives this has got an extensive catalog. This is Messier objects, but it goes into all kinds of things. And it'll tells you what is good to look at tonight, what you might want to look at some other time. There are all kinds of ways to slice and dice the data in here. But for us, it's going to be a game changer to showing the general public what we can do. Honestly, this thing does incredibly well in light pollution too. It has the built-in light pollution filters, and it in the middle of the city, in a school parking lot, that sort of thing. This is going to be a game changer for us in trying to stir interest in younger people about what's out there to consider looking at. Meryl, you got anything else you want to?
Just talk about light pollution. They did the YouTube video in downtown Las Vegas.
Yeah, the thing that caught us about this that said we really need to try this out was a YouTube video of a couple that had set one of these up in downtown Las Vegas and had gotten incredible results with it. So that's our real-time observing in Memphis, Tennessee tonight. So Jeremy, back to you.
Excellent, guys. Thank you very much for that demonstration. We do have a couple of questions. Can you change the exposure duration of the images?
Can you change the exposure duration? No, but of course, how long you leave it pointed at something dictates how much resolution you get. Because it just stacks the images.
It's still stacking right now.
Yeah.
Okay. And again, you don't have to do any polar alignment. You don't have to do any plate solving. You don't have to do any pre-setup. This is literally set it down, plug it in, push a button, and it goes to work. I mean, it is essentially a smart telescope.
Exactly, a robot.
And yeah, I mean, you were talking about outreach. You know, I had the Orion Nebula in my eyepiece last week. You have lines of people wanting to come up and take a look. You guys had it plugged into a monitor, and you can not only show them the image, but you can actually see some color detail as well. So it really is pretty cool. And also another interesting thing, not everyone can make it to the eyepiece. Of course, we have, you know, issues with young children that can, you know, that we can get up there, but it was also brought to my attention recently about handicapped people and trying to find ways to make this accessible to handicapped people. This will also be a game changer for us in that regard, where we can basically show anyone an image of something that this telescope is pointing to.
And it was years of doing this for Boy Scout troops that convinced me I needed something other than a bunch of Boy Scouts standing in line to look through the eyepiece.
And the other advantage is you can do it on your own iPhone. I mean, it broadcasts to up to 10 devices, iPhone, iPads. So you up to about 30 some feet away. So whatever you can't get around the screen, they can do it on their own device.
So if they have the app on their phone, they could walk up to this device, plug in an object they want to see, M2, and bam, it'll slew to it.
Well, no, whoever, like this, in this case, Jeremy's iPad's in control, all they can do is observe.
Okay.
Now, Jeremy can do that, or whoever's got the control app. Basically, it's the first one who signs on.
Another question, are you able to dark correct and flat field the images?
Nope.
Okay.
I'm not sure.
I'm not sure why we would,
Yeah,
but
for
I mean,
observing, I don't think you do that.
they're color images. You can take it. You can save the images and take them into another program and manipulate them if you want to. If you think they're noisy, you can try to denoise them. But
did you save M81?
Huh?
Did you? I mean, M31.
Did I save it?
Yeah, we the other night we tried M31 and we kept it on for about 8 minutes and had a nice detailed color cut.
Yeah.
So it's pretty amazing.
But I'm not sure how I would get to it to show it. So.
And the app, what is the app called Stellina, or is
No, the app is called Singularity.
Singularity? Okay.
And Vanos is the name of the company.
VANIOS is probably Vanet. It's a French company.
Yeah.
Okay. What about viewing the sun and moon? Would this be a good telescope for that too?
The moon, yes. The sun, no.
No, we were hoping to show you the moon.
It got down below the edge of the house.
I can't. It's just too far west. But yeah, it's great for the moon. Sun, no.
Yeah. Tonight would be a good night for the moon too. We've got a thin crescent.
Right.
We were just too late.
Okay. Well, thank you very much, Meryl and Rick. At this point, I'm going to turn it back over to Billy.
We're going to turn on the heat and wish y'all a good night.
Hey, I do have a couple of questions that popped in my head as I was watching this. I mean, that was an amazing demonstration, and I think that really captivated a lot of people at home because we got a lot of really great comments from everyone about how amazing that was, especially with such a short exposure. But going back to that question about the sun, if, for example, you set it down and you say, "Hey, go to the sun," will it tell you no, or do you have the option of saying, "Okay, I put a solar filter on you. Now go to the sun," and it will do that?
We don't know, and there's really no way to mount a filter on there. Okay. So we suspect the software would keep that from happening.
Okay.
I doubt that's an option.
Okay. So this one is totally for astrophotography. It doesn't have the capability to have an eyepiece on it, does it?
No, not at all.
Okay. And let's see. One other I had was, so you mentioned that if you're in a really light polluted area, it already has built-in light pollution filters. Does it always have those engaged, or does it basically kind of gauge the ambient light that it's in, or base it on what it's looking at, or what?
I'd be willing to bet it's always engaged, but we don't know that for sure.
But I think
Okay. Yeah, and there was a question about if you'd ever considered dual broadcasting on Twitch. I think we might have had some chatter in the chat about that, but is that a consideration that you all have thought about?
I don't know what Twitch is.
we only had just a week and a half, so we got a lot of time to play.
Yeah. First things first. Let's get some.
Yeah, this is actually our first live internet demo. The first live event was a public showing.
That's right.
Yeah, at the Pink Palace. And the trick with that, of course, is a monitor. I've used a 32-inch monitor, and I've got a battery system set up to run it on, so we can go out without any kind of AC power and set this up and run it all, and independent of where we're at. So that's the part that we're really tickled about. This will be good for just about any condition. Somebody wants to say, we want to set up a public observing session. Come show our Boy Scouts, our Cub Scouts, our school kids, the public. This Planet Memphis Pink Palace Museum also has a planetarium, so that's kind of our connection with them. And so whenever they have public observing sessions, this will be something we can use there too.
The unit itself has a 5-hour battery life, and you can actually get extra battery so that all night long if you want to, just the unit itself.
Oh wow!
Now,
Okay.
And so the enhancement that Rick did was the screen, and you make that as big as you want because it's an HDMI output.
Yeah, and I'm just running that off my iPad. So I've got an HDMI output for my iPad that I'm running over to this screen.
Okay, so then the unit, aside from if you had to plug it into an AC, which you said you don't, it's totally disconnected from everything.
Yeah,
Yes.
You probably saw it off in the distance, but it's all by itself, and except the heater is trying to keep it warm.
You connect to it. You connect to the telescope by Wi-Fi, and then of course we're using cellular to connect to the Zoom call.
Okay.
It has its own Wi-Fi broadcast.
All right. Well, thank you guys so much. That was a really fun demo. And like I said, we got so many great comments in the chat. So thank you for taking the time and going out in the cold weather to give us a demonstration of that. That was really neat.
Glad we could do it. Thank y'all.
Thank you. All righty. So now we are going to go up to Illinois, and we're going to visit with Dr. John Martin, who is an associate professor of astronomy and physics at the University of Illinois at Springfield. And he's going to talk to us a little bit more about what's up in the sky. So, John?
How do I follow that? That was amazing, guys. Wow. Well, I'm really pleased to actually be invited to get a guest at the star party here. UIS Observatory and Dyer Observatory have been Twitter friends for a while, and it's really good to be just here and contributing in person. I promised tonight a picture of the Flame and Horsehead Nebula. We hope to do it live, but well, you guys might have heard there was a snowstorm up north here in Illinois, and we have about a foot of snow on our road, and the township has not cleared it yet. And I got some clouds tonight too. But about 2 weeks ago, we had taken this picture, and so I can share it. We got here the Flame and the Horsehead. So I'll point out, just so that you guys are oriented, the star in the middle, the brightest one, is the leftmost star in Orion's belt. And this other bright star up here is the middle star in Orion's belt. So Elnatek and Elinam. And you can see here the Flame Nebula. And then down on the bottom, you can see the Horsehead. The red colors in these nebula are because the hydrogen atoms are being ionized in these clouds of gas by the other hot stars nearby. And when the electrons recombine with the hydrogen atoms, it causes this red glow. The dark parts then of these clouds are other darker material in the foreground that is blocking the illumination behind. This picture was taken, well, I'll talk a little about our observatory in a second, but this picture was taken, we like to call this our $400 wide field camera. We basically have an ASI 178 CMOS, not cooled color camera attached to a cheap Orion guide telescope. But it gives us a beautiful 1 by 2 degree field to get shots like this. This one was 60-second stacked images over the course of about 20 minutes stacked together. So we get some nice stuff. And I'll have our Twitter handle up there for anybody else that wants to follow kind of in the things we do with that. You know, my angle on Orion is that I'm a massive stars astronomer. So I want to talk a little about, and thanks for Dr. Billy for inviting us. I want to talk a little about the UIS Observatory to just let people know about who we are. We're the Henry Barber Research Observatory at the University of Illinois Springfield. University of Illinois Springfield is part of the University of Illinois. We are the smallest campus in the system. We are based in the state capital of Springfield. And you have now tonight met the entire astronomy physics program at UIS. We're very teaching focused, but we have also been endowed by our community with this great research observatory. I also do research. It's named after Henry Barber, who during World War II, he was a Army Air Force aviator, and he learned how to navigate. His love for astronomy started by learning how to navigate in planes using the night sky and the stars in the sky. And through his life, he was never a professional astronomer, but he was always very interested in astronomy. And we have lots of people in the Springfield area who are interested and have supported our research. And kind of as a thank you to them, we also have a big kind of public outreach program. This is a picture of our observatory with the 2 domes. This is actually a better night sky picture of our observatory. We're actually in a fairly dark site. People might think of Chicago when they think of Illinois, but we are the Prairie State. And here in central Illinois, even if you're in the city of 100,000 like Springfield, you can pick a direction and drive 20 minutes and get a nice dark sky like this, where you can see the Milky Way pop out in the evening sky. And we've again got the 2 domes open. You can see this night the 20-inch dome was open, 16-inch was closed. We have 2 telescopes at our research observatory, a 20-inch and a 16-inch telescope. The 20-inch has instruments, it has an imager, it has 2 spectrographs. The 16-inch telescope we use mainly to do bright star photometry. You know, this is something that a lot of professional astronomers actually ignore because a lot of the brightest stars are just too bright for the largest telescopes out there. We use our 16-inch to actually follow and do photometry on bright stars and contribute to the the American Association of Variable Star Observers and their efforts to track the changes in brightness of the brightest stars we see in the sky. My interest, though, what I love about astronomy, my specialty is massive stars. And this is one of the few pictures that I did not take. This is a picture of Eta Carina taken with the Hubble Space Telescope. And this is one of my favorite stars because I'm as an astronomer interested in the most massive and large and luminous stars in the universe. Actually, Orion, it's great we're talking about Orion tonight because Orion has a collection of a lot of these massive, bright, hot stars. Now, these stars are important because they actually make in their cores the heaviest elements in the universe. You know, the iron in your blood, the calcium in your bones, the silicon in your fingernails, these atoms were made inside large luminous stars. I'm most interested as an astronomer in how these elements made inside these stars get out. Why don't they end up trapped in the remnant at the end of their lives? How does it get out? How does it get out, spend 4.5 billion years floating around, and then start asking questions about where it came from? So that's what really interests me. Orion is great for this. But, you know, actually it turns out that we still have not learned about a lot about these stars. Oh, I noticed I had an animation in there I didn't know about. I forgot about. we don't know a lot about these most luminous stars, even though we can see several of them with our naked eye in the sky in Orion. The reason for this is there are literally, millions of fewer massive stars than stars like our sun. We've figured out stars like our sun and the life cycle of stars like our sun pretty well, just because there are so many of them out there. And we can look at star clusters and learn about how they move around the HR diagram as they age and they become red giants and then planetary nebula. But with very bright luminous stars, there are many fewer of them. Many fewer of those are formed in every galaxy. And so we just haven't sorted them out as well. And if we look at the top of the HR diagram, we see just, like whole mess and convolution of different types of stars. And we don't even know how like some of them are related to each other. Like, is this stage after this stage? We don't know. We're kind of guessing. Let me get my yellow and red supergiants up here. I mean, we've got kind of some questions about which of these go supernova even. There's some research out there to show that actually there might be an upper mass limit to stars that go supernova. That's kind of interesting. We know that the most massive stars, they do this really weird thing called supernova imposters. Like Eta Carina. Eta Carina was a star that started at 120 times the mass of our sun. In the 1850s, it underwent an eruption where it became visually as bright as a supernova for 5 years. And then afterwards, it threw off about 20 solar masses worth of itself, about, just under 20% of its mass into an expanding nebula around it. And it survived. What's up with that? There are lots of instabilities and things going on up here at the top of the HR diagram that we just don't know. This is what interests me and makes me excited about these stars. Now, Orion is a great place to see them with your eyes, but actually studying the ones in our galaxy is a bit problematic because the plane of our galaxy is filled with a lot of gas and dust. So a project that I've been running since 2012 here at the UIS Observatory, and we started it with an NSF grant. So I'm sure most of you guys are federal taxpayers, so I want to thank you for helping me start this project at one point. But we are taking pictures of the Andromeda Galaxy and the Pinwheel Galaxy and tracking the most luminous and massive stars in those galaxies to see what they are doing. We are right now watching the next supernova or next supernova imposter in these galaxies. And watching them and keeping track of what they do so that when they pop off, we're ready. I want to add, this is a point of pride for us, that actually this survey we're doing at the UIS Observatory is actually the longest continuous multi-filter survey of the Andromeda Galaxy and the Pinwheel Galaxy. We're the record holder right now. And as long as I keep going, I think we'll be the record holder in the future. And I will point out, this is a picture of the Andromeda Galaxy that was taken with that same camera we used to take the picture of the Flame and the Horsehead Nebula. And I have on the bottom our website for this project, because all the data we do from this project is actually out there and publicly available for people to see. And so please feel free to go and explore your favorite stars in the Andromeda Galaxy and the Triangulum Galaxy. And if you don't see your favorite star in there, I might have been recording it in the images all along. Let me know. I might be able to pull out the data for you. I'd like to tell the professional astronomers that as well. And so that's basically the rundown of what we do. I'm going to just take us back to that fabulous picture we had of the Flame and the Horsehead Nebula. And if people have questions, I'm happy to answer them. Thanks again for inviting me tonight.
Well, thank you, Dr. Martin. It's a pleasure to have you tonight. I hope you're going to be joining us in the future again. So first of all, big congrats on having the longest running survey of multi-band photometry for M31 and M33.
Yeah.
But when you were talking about photometry, can you talk a little bit about what that means?
Oh, yeah. So it is measuring in a calibrated way the brightness of a star. And when we do that, when we talk about filters, multi-band filters, so we don't just measure the total brightness of the star we can see. We'll pass it through a piece of glass that actually lets through just specific wavelengths of light. So like green or blue or red, a little more scientific than that. But then we will measure absolutely the brightness of the star in that filter. And that tells us information about how luminous the star is. And when we take in the photometry and measure its brightness in more than one filter, we can do things like estimate its temperature or tell other things about the star. And some of these stars are really interesting. They actually change their colors a little as they go through their activity. So multi-filter photometry is actually very important for understanding these. Yeah.
Awesome. And we had a question come in. Are there ways that amateur astrophotographers could help with the survey?
Oh, well, my advice, I try to do a lot of work with non-professional. I like non-professional as a term because a lot of these people in their backyards are actually doing some pretty good work. And my advice to them is there are a couple resources out there. The first one is the AAVSO, the American Association of Variable Star Observers, is a great organization to look up and get interested in if you're interested in contributing to science of stars. And my advice to the non-professionals in their backyard is the most impact they can make often is if they pick a star that they adopt as theirs. And they spend a lot of time on that because, us professionals can sometimes be real flighty and not want to spend years on something. But the people in their backyard, they don't have to go through the telescope allocation committee. They can keep working on something for very long baselines, and that's often where they can contribute the most.
Nice. And when you had mentioned AAVSO, it also brought to mind you don't have to have a complicated setup to be able to contribute data to the AAVSO, do you? I mean,
no, you can even do it with your eyes. Yeah, because I teach. This is a great thing. You can train your eyes to actually be photometers now, and you can actually observe stars visually and estimate their brightness with or without a telescope. And the AAVSO has some great resources to teach people to do that.
Nice. And then all your data is going into a big database and you're contributing to science that's being done. So
right. Yeah. Anybody in their backyard can be doing that. Yeah.
Yeah. So especially for some of our budding astronomers that want to see what kind of, things, what their appetite, that might be a fun project.
I'll try to find the link for the 12-star tutorial that the AAVSO has. I'll put it in the chat so you can get that on YouTube.
Awesome. Let's see, there was another question that came in. This one's really pertinent nowadays. Do satellites get in the way of observations? 35 more are being released by SpaceX, possibly.
Oh my gosh. Yeah. I love to. I don't have it in this slide deck. Another time when I visit Star Party, I'll bring this along. But we actually have been photobombed by 747s flying through before. I'll tell you that for the imaging we do, the Andromeda Galaxy is positioned usually in a place where we are imaging it usually in the middle of the night. So anything flying overhead in low Earth orbit is not getting in the way. So the work we do, not as much. But yeah, when you're trying to image something, a couple hours after sunset, or maybe even further away from sunset in the summertime, if you're at a high latitude, this is something we see. We see satellites going through. And I remember this summer, we probably threw away a couple images because we got photobombed either by an airplane or a satellite. It happens, unfortunately. Mm-hmm. It's happening more often too now. Yeah.
Okay. All right. Well, thank you so much. That was really interesting. And I hope that you're going to be able to continue this survey for many more years and continue holding that record.
And hopefully we will come back with some live telescope views another day.
Yes, exactly. That's what I'm hoping to as well, because I'm at home right now, but I'd like to be up in our dome giving some live views. So Fingers crossed for next time, right?
Yep. Thank you.
All righty. So now we're going to come back into Tennessee, and we're going to join Theo Wellington, who is a member of the Barnard Seaford Astronomical Society right here in Nashville. And, you know, we've just been talking about with Dr. Martin some of those really massive stars, but now we're going to go to the other side of the spectrum, so to speak, and talk about some really small objects. So, Theo, what do you have for us?
All right. And John, I will say that Betelgeuse has been my favorite star since I was a teenager. Yeah, it's a great one. I follow it on Twitter. That's the most ridiculous thing. Okay, let me see if I can share my screen. Screen one. Okay. Share. Oh, share. Okay. You see my screen?
Yep, you're good.
All right. So we're going to talk a little bit, about the small guys. And my subtitle here is "Who Get No Respect Unless They're Coming to Get You." So that's kind of foreshadowing there. All right. Let's see if I can make this work. And okay. Boy, people want to call me when I don't want to be called. Okay. You going to advance? I switched which the screen I was on, and now it's not. There we go. All right. So, there's cool things to look at. There's great big things. There's really bright things, but there are a lot of tiny things that you can look at, just usually not with your eyes out there in space. So we're going to start with the small things here in the solar system. And my idea for tonight actually started out with something that ended up in a sort of a minor fail. And that's fun, but as my astronomy professor used to say, thereby hangs a tale. All right, so these are asteroids, and this is just a sampling. This is what they look like when you go visit them with your spacecraft. They're not to scale whatsoever, because the guy there, the big guy on the left, is Vesta, and that is much, much larger than tiny little Bennu over on the other side. But Bennu is cool because we visited it. We took samples, which are currently on their way back. And it's also cool because Bennu is also at the top of the list for things that are dangerous out there in space. It's not a civilization ender or dinosaur killer, but it would definitely leave a mark. We're also, we just launched a spacecraft called Lucy, which is going to visit the Trojan asteroids of Jupiter. And later on this year, we're launching Psyche, which I think is a really cool mission to a metal asteroid. So it may look a lot different from these here. And these look kind of the same, but not exactly the same. They're all a little bit different, which is cool. But when I looked up to see what's up in the night sky that I would possibly share out of this group, right there under the Pleiades, just above Orion, is the cute little, well, it's not cute, it's not little really, but this is Asteroid One Series. So it's the largest asteroid. It's over 900 kilometers large, so, moon-sized, give or take. Asteroid, by the way, is a terrible name coined by William Herschel. It means star-like because when he looked at these things, he couldn't resolve them. They're always just dots that look like stars. Now, when Ceres was found, it was kind of the answer to a problem, because when you look at the solar system, there's kind of this regular spacing thing that goes on with the planets. And you get to Mars, and there's this gap until you get to Jupiter. So once we got telescopes working well, people started looking because there should be something there. And they found Ceres. Great, a planet, where we thought it would be. And then they found another one, and another one. And eventually there were like 11 planets until people finally said, wait, there's hundreds of these things. And of course, there's thousands, if not millions. So Ceres and all the rest of the lot got demoted. So they were called minor planets or asteroids. And if that's a familiar story, so it got demoted. And then after some recent controversial classification shenanigans, Ceres, being round, got a promotion to dwarf planet. So speaking of Pluto, today is also Clyde Tombaugh's birthday. So a shout out to the discoverer of Pluto, who thereby started the discovery of the rest of the solar system. Now for the inner solar system, Ceres is pretty cool, and it's got those bright patches on it that were kind of interesting. And luckily, when our spacecraft went there, it could get low enough and had good enough instrumentation to figure out what that is. And it looks like it's salts left behind on the surface, you know, when some really salty water oozed up through the surface. We had kind of thought all these worlds would be completely dead, would just look like the moon, a bunch of craters, that things shouldn't happen on them, or maybe not very recently. So this was kind of cool that it's a different place, that things are happening on more recent than 4 billion years ago timescales. So it's a big enough thing to be differentiated. You know, we had the talk about the structure of exoplanets. So Ceres has structure. It has a crust, it has a middle part, and then it has a rocky core. So I think it deserves the upvote to dwarf planet there. Now these images are courtesy of the Dawn spacecraft, which is still in a stable orbit around Ceres. You could say we gave it an artificial moon. So Monday night was the last clear and reasonably warm night. I said, hey, let's go find Ceres in the night sky. Pretty bright. You know, you can't see it with your eyeball, but it's just not far under that. So, okay. Pointed the telescope, said, go to Ceres, and, well, that's a bunch of stars, but there's no obviously bright thing there that's Ceres. So clean miss. And that was kind of weird because I looked at some other things that night. And when I told the telescope, go there, the thing I was looking for was there. So I have a little mystery on my hands to solve of why wasn't I finding Ceres and where exactly is it, which we'll have to wait for the next clear and not blazingly cold night to figure out. But all is not lost, because back in the archives, once upon a time, we looked for Vesta, which is also pretty bright. And I took 2 images an hour apart and made a little animated GIF out of them, so you can see how much it moves in just an hour. And that's how we found these things, because they move in a noticeable way, often on short time scales. So you can look at the night sky, take pictures, and pick out the thing that moves. This is kind of the same thing that Clyde Tombaugh was doing to find Pluto. He was blinking between 2 different views of the sky, except his were taken months apart, not just an hour apart. And then I got ridiculously lucky and had a second clear night. I have to be patient because sometimes there we go. So now I was able to show not just the difference in an hour, but the difference in a day's worth of movement. So that's what it looks like to look at an asteroid. It's just a bright dot, but it does move. Now, occasionally they swing by a little bit close. This, let's see, Vesta, I say it's about 200 million miles away, give or take, depending on which side of the sun we're on. It's a pretty long way off. We had in 2017, an object called 3200 Phaethon came by, and you can see it there tooling across the screen. This is a series of images I took over probably 2 or 3 hours. And it just gently moved across the field of view. And when things are close and moving pretty fast, that's something you can see in a telescope eyepiece. You can zoom in and get the field narrow enough to where you can watch it move. So that's pretty cool. But, you know, unless we send a spacecraft there, how would we know what it looks like, how big it is? You know, what kind of shape does it have? Well, it turns out there's 2 kind of fun ways to do that. The Arecibo telescope had the ability to actively send radar up and then listen for the echo to ping things going by and get their shape. So that's kind of cool. So it's done that for several asteroids. And this happened to be 3200 Phaethon. The other thing you can do, and this is a cool amateur thing, is you can watch an object occult go in front of a star. And if you space a whole bunch of observers along that path at different places, each observer is going to see that star wink out for a different length of time. And when you combine that, you end up kind of making the shadow of what you were looking at. So this is what happened when they did it for 90 Antiope, which is a double asteroid pair. And this is really cool because you can see the shape of it. The other fun group of small solar system objects are comets. Now, these are known since antiquity because unlike the invisible asteroids, comets, when they come towards the sun, become visible. They're not any bigger, but they get these ridiculously long dust and gas tails that we can see quite well. So the classic word that gets used a lot of times now in what I'll call the clickbait press for anything moving through space is hurtling. Everything hurtles. And comets, I think, are the ones who deserve this. When they're coming into the inner solar system, they really are moving fast. Most near-Earth asteroids really are going about the same speed we are. There's just a little bit of difference, but comets are really booking. Now, if you look closely at this picture, you're going to notice that each of the images of the stars, because I stacked the images on the comet and let the stars trail, but each one of them looks like a little exclamation point because there's a gap. So that gap was the frame where I kicked the telescope. So I threw that one out. Oh, well. But still, that's pretty cool. So that makes the speed effect there. And then sometimes you can do the same thing I did for the asteroids, which is you just run the series of images together in a little movie. So here's the recent Comet Leonard. It had a fun encounter with two relatively bright galaxies. And so over about 2 hours, you could again watch the movement of it because it was coming by pretty close. Now, comets also give us meteor showers as Earth passes through those long streams of dust that get left behind by those tails. And we have visited a few of these guys up close and personal. They're fun because they're pretty much not round. And in particular, we visited this one here. He's down in the lower corner. This was a really cold night, so I didn't wait around really to see how well centered it was. I just took pictures. So this is Comet 67P. It was the same night Comet Leonard was going by the galaxies, so that was fun. The reason why there's all that light on the one side of the frame is the darn moon, but it was the clear night that Leonard was going past the galaxies. So 67P is fun because we did have a cool mission. And when the Rosetta spacecraft got close, it took this picture. And everybody looked at that and a few others as it was rotating and said, rubber duck. It's just a pretty funny thing to think of a comet as being, but okay. When we got a little closer, and not so much of a rubber ducky. But it was a cool mission. We met the comet on its way in and stayed with it as it rounded the sun and on its way back out. So we got to see it become more and more active, which included cool footage like this from one of the cameras. The long streaks are mostly cosmic rays, but you're seeing just dust and stuff hit the detector. It looks like a little snow blizzard going on there. So that's a view of a comet that we don't normally get. And here it was the same night that I could not find Sirius. The telescope had no problem putting the comet in the middle of the frame. A little bit further out, but still looking good in the night sky there. All right. So currently, one of the things I like about this comet is I feel a little personally connected to it. Comets, when they come in, sometimes get their orbits changed. And the biggest orbital changer is our good buddy, Jupiter. So ever since then, it's been part of what we call the Jupiter family of comets. It travels out a little further than Jupiter and comes in currently a little further out than we are. But if you've met Jupiter once, you're going to meet it again. And so every so often, it gets its orbit changed. The last change happened the year I was born. The next change will happen in 2220. And that change, we expect it will put the perihelion, the closest approach of the comet, somewhere inside of our orbit. So that could get fun. And some of the things that are classed as asteroids occasionally look a little unasteroidal. This is 596 Sheila, and here it is giving off some gas and dusts. So we've been wondering what's up with those kinds of things. And remember our good buddy Phaethon that we watched coming in. This is a view from stereo A where it was looking and saying, you know, there's a little bit of a tail going on there. So that's kind of interesting. And the orbit of that particular rock also traces out the stream of gas and dust that we see every year as the Geminid meteor shower. So 3200 Phaethon is considered the body that originates that, even though today when we look at it, it really doesn't look much like a comet. So maybe some of the things we see as asteroids are kind of comets that have just lost almost all their gas and dust over the years. So that's kind of cool too. But if asteroids are just dots that you need a telescope to see, why do we even care? Well, for scientists, these are bits left over from the early days of the solar system. So they have a lot to tell us about what things were like at the beginning and how the process of planet formation happened. The planets themselves have undergone so many changes that a lot of the early stuff has kind of been erased. So comets also are pristine bits that are from the outer solar system where it was mostly ices and only some gas and dust. So everything tells us a story about what went on back when those objects were formed very early on in the solar system. So they're cool for that. Amateurs, again, also enjoy these. It's kind of a challenge. Can you find it before the survey telescopes do these days? We had a member of the BSAS lived in Decatur, Alabama. That was his hobby for many years, was finding asteroids. And he actually discovered 125 over the years. So that's pretty fun. Generally, you get to suggest the name of an asteroid if you find it. If you find a comet, it gets named after you. So that's some good reason for having some fun with these small bodies. And then there are the practical reasons. You know, sometimes the Earth crosses paths with asteroids, and if they're big enough, they leave a mark. This is luckily an infrequent occurrence. Small stuff comes in and rarely reaches the ground. But you know, we have the internet these days, and the internet has a lot of fun with this. A huge asteroid, another huge asteroid, an asteroid barely missed. And by the way, this barely missed guy was 6 foot large. 5 asteroids which could possibly hit Earth. Killer asteroid. An asteroid warning. And it's always NASA that takes the heat for these. And invariably, the picture that they use to accompany these articles is something like that. So, oh my goodness, we're all going to die. But no, actually, nothing we know of is going to hit. So not for the next 100 or 200 years. The other fun thing about these small dudes is that they get messed with by all the big stuff in the solar system. So you can't run their orbits out forever. They do move around, they get pushed around, but still, for the next little while, we don't have anybody that's supposed to hit. But if you want to worry, I don't recommend it, but if you want to, spaceweather.com has a nice list every day of who's coming in, how much they'll miss by, expressed as distance to the moon. So if you see a 1, that's what the distance to the moon is, how far it's going to miss us by, and the rough guess of how big it is. Now, for people that we haven't gone to see, for the asteroids we're not visited, how big is it is kind of a guess. It's an educated guess, but it's how bright is it and how far away is it? And if they all reflect light about the same, you know, you can kind of make a good estimate of how big. So that's what we know about. And we got no hits. But we want to be prepared. So on November 24th, we launched a spacecraft in the general direction of asteroid Didymos and its tiny moon Dimorphos. And it's called the DART mission, which I think is pretty fun, the Double Asteroid Redirection Test. And we're just going to ram into the small moon of a larger asteroid and see if we can change that little moon's orbit any tiny bit. We have a little CubeSat that's going out with us that it'll let go about 10 days before impact. So hopefully we can watch what we do. But that's it. We're just going to ram an asteroid. It won't look half as cool as anything happened in a movie, but we'll see what we get, because there's a lot of unknowns in how that material will absorb the impact. How much can we push it? So we're going to change it probably a very small bit, but we think we can do it a measurable small bit. So that's going to be a little bit of fun. The actual collision is supposed to happen between September 26th and October the 2nd of this year. And that might make a fun event to watch that happen if we can. And the European Space Agency also plans to have a follow-up mission to assess those changes in 2027. I might have to go look up and see if we can find the bigger one in the night sky. And we've heard a lot about Lagrange points. Never would I have imagined that there would be so much chatter in regular newspapers and such about Lagrange points. For the Earth-Sun system, there are 5 points where the gravitational forces are kind of balanced, and you can put things there and not have to spend a lot of energy to maintain them there. So we just sent the James Webb Telescope to L2. L1, I think, I think that's where the Discover satellite is that takes lovely full frame images of the Earth. L4 and L5 are 2 points where you can collect space junk. Jupiter has a lot of space junk at its 2 L4 and L5 Lagrange points, and we call those the Trojan asteroids of Jupiter. Funnily enough, the one group is called the Trojans, and the other group are called the Greeks. Astronomers have a sense of humor, they really do. So we thought, well, we should have some too. I mean, yeah, we're not Jupiter, we don't have that much gravity, but still. And after much, much, much looking, we've found so far 2. 2010 TK7, and there's its dot picture. And they just announced a few days ago, 2020 XL5, and it would look pretty much the same. So that's cool. It was 2020 tells you that's when it was actually discovered, but till they wrote up the paper and, looked at other observations to get a good idea, make sure it is indeed a Trojan asteroid, they just now published the paper. So they think it's stable there for the next 4,000 years. So we do have some little Trojan asteroids collected up. So that's a lot of fun. So generally, they're just out there. We can't see them well, except in pictures. But still, they're part of our solar system and they have a lot of cool things to teach us. But remember I said, they don't get respect unless they come looking for you. So mark your calendars, okay? April 13th, and yeah, it's a Friday the 13th, 2029. We are going to have some fun. Asteroid 99942 Apophis, which is a great name, right? It's going to tool across the sky because it's going to come so close that you will be able to see it with just your eyeball. Binoculars will help, especially in the city, but you'll actually be able to watch an asteroid with your eye move visually over the course of the night. This is sped up just a little bit. I think for most of it, it's about 2 minutes a second, but still, it'll be in the constellation of Cancer, which is the invisible thing for us in between Gemini, the twins, and Leo, the lion. So it'll be coming up pretty nice and high by April. So easily visible in the night sky. Sadly, here in Nashville, we won't be able to see the moment of closest approach, which is only 19,600 miles. That's inside the geosynchronous ring of satellites. That's, in astronomical terms, very, very close. But it will, I promise you, miss. Right now, we've worked on this, and the confidence level, we're pretty sure we know how far it will be within a couple of meters, which is really good. So we're not worried about it hitting. But, you've seen the headlines with just normal stuff that's missing by 1,000,000 miles. I imagine this is going to go crazy on the internet. So it'll be a lot of fun. Since we won't see it at close approach, you can watch it coming the night before. And I assure you that on the evening of Friday the 13th, we'll wave at it as it heads back out. So that's kind of fun. If you Google it, one of the people also ask questions is, which country will it hit? And again, none of them. It's just going to be good fun. Have an end of the world party. It'll be good fun. So I hope you've enjoyed hearing about some of the small stuff in our own backyard. Let me stop sharing here. And what I would like to say is the next not too cold night, I'm going to go find Sirius because that's really bugging me now. And in contrast to a current movie, do look up. There we go.
All right. Thank you so much, Theo. That was a lot of fun. And you've always got great stories about your observing sessions. So I need to go observing with you sometime because who knows what we're going to do. We do have some questions that came in. So the first one was Umau, or what was Umau? And did it hurtle or did it careen? Did it zoom by? What happened?
Ooh, how's spelling on that? Oh,
I believe that was the one that, it was supposed to be interstellar, if I remember correctly.
Oh, that dude. Yeah.
Yeah.
I wish they would give them slightly more pronounceable names. That was definitely doing some hurtling. I mean, it's going fast enough that it's not, it couldn't get captured by the sun. It headed back out into interstellar space. There's still some chatter. I saw somewhere there were some, if you had enough money, right? Hey, Elon, don't you have some spare cash? Anyway, to actually go catch up with it to see what is this thing and why does it kind of look weird. Best guess is it was really long and skinny and tumbling in a fun way. But, of course, when something comes in and goes out like that, it's like, wait, maybe the aliens just popped in and had a look, Maybe that's their Voyager spacecraft that, is just tooling around. So, yeah, that was a fun thing. And since then, and of course, you don't see anything until you look. And so since then, we've noticed a couple of comets that, like Comet Leonard, it came into the sun from an 80,000 year orbit, so it had a long fall, and it got ejected. So it'll never be back. So we eject things, and they're going to go somewhere else. And so you just never do know. But yeah, I would call it hurtling. I always look for the word in the stories because it's almost always there.
Yeah, I think for Apophis, when it comes by, they're going to have to come up with a whole new synonym because hurtling just isn't going to do it justice. So,
it's that's going to be a lot of fun.
Yeah.
And I will be selling end of the world T-shirts with all the different ends of the worlds that I have currently lived through. So,
yeah, end of the world helmets, all kinds of things, right? There's some other questions. What is comet ice made of? Is it water like on the Earth?
Yeah, most of it is water ice. There's some CO2, but an awful lot of it is just plain water. And the only thing we look for that's interesting is we're looking for the isotope balance. So hydrogen can be just, a single proton with an electron, but it can also have a neutron associated with it, and you can have deuterium. And on Earth, our water has a certain ratio of that. And so we were interested in, do comets share that same ratio? Because that is a clue about where the water on Earth came from. And a lot of theories say, well, Earth was hot, so maybe it evaporated a lot of its early water, and then the comets that would have been much more numerous, kind of gave us back a pile of water. Interestingly, some comets don't have the same ratio as Earth, but some do. So that's still an open question.
And that particular kind of water is known as heavy water, correct?
Yep.
All right. Let me see here. Do you think more probes will launch sub-probes with cameras just to see what happens after this, like with the DART mission?
Yes.
I personally I hope they do.
Yeah. Because it's fun, right?
Yeah.
And the only real reason they didn't do it with the Webb is because there was already so much complexity that just did not need any more.
Yeah, I'd read about how they had thought about putting different cameras on different things to see if various parts deployed, but when they did the analysis, it was like, well, we're not really going to be able to see anything with these cameras. So why, like you say, why add to the complexity and the cost even more, which ultimately is going to add to the rocket cost and things like that. Let's see, I thought that there was another one on here. Oh, I think this is referring to Apophis. So when it comes through, is it going to be moving slower than the ISS?
Yes, the ISS is so close to us. I mean, that's only a few hundred miles above our heads when it's going, overhead, and Apophis is still going to be 19,000 miles away. So even though it's moving faster velocity wise, you're not going to see that kind of motion. The ISS only takes about 5 minutes to cross the sky. And it'll be a couple of nights distance, I guess, because I looked at where is it the night before. It's roughly crossing about a constellation a night, something like that at close approach. So if that gives you sort of a bookmark for how much movement in a given night.
Actually, that brings up a question I had. So you were saying that it should be visible naked eye. So obviously when it's farther out, it's not going to be visible naked eye, and finally it gets close enough where it is within that threshold. So is it within that period of naked eye visibility for long enough that, it's essentially at least 24 hours so that the entire Earth could rotate and people on all parts of the globe be able to see it naked eye?
I think so. I expect to see it, like I said, the night before and the night after. It'll be interesting to see. Somebody will come up with a light curve eventually to decide, when is it going to cross, say, people use 6 magnitude as a visual limit, but, here in the city, that's 4th might be a much better. And if it's moving, you'll see it. I mean, there's a lot of satellites you can see at that magnitude. So somebody will figure it out. I do expect there will be cruises and trips to where you can watch it at the moment of closest approach, and everybody can cheer when it doesn't impact. So, I mean, that's going to be some fun.
Yeah, be sure to get Apophis insurance, I guess. Jeremy Veldman mentioned that Apophis was discovered by Roy Tucker, who was a former Memphis Astronomical Society member. So very cool. So right here from Tennessee.
There you go.
Let's see. And I think the last question that we have is, you've shown us a lot of the images that you've taken with your telescopes and your cameras. Do you have a preferred telescope for someone wanting to get into astronomy on a budget?
That's a.
And this might be something we want to open up to the whole group.
Yeah. Dobbs, the ones that they move up and down and back and forth. They're really simple. You pointed at what you want to look at, biggest bang for your buck. And honestly, look for used stuff, because people buy things, they sit in the closet, and then finally they get rid of them. You can get a lot of used stuff. You might even try contacting your local astronomy club and see if they have something they want to get rid of, because we get donations all the time, and it gets a point where you can't really take any more. So those are really good. They're great for just visual observation because they don't have setup time. Now that Stellina thing they've got there is cute, but it's not cheap. So there's sort of a trade-off there too.
Probably want to mention about. Sorry, you probably want to mention a pair of binoculars is a great place for people to start too.
Yes, and if you're looking for something to do with kids, I think that's always good. You might get a stand because it's hard like heck to be able to stabilize them. But binoculars are just little telescopes, and they're more natural to use because you're using both eyes. And they will bring out some of the things that we would see if only we had a dark sky, like the Andromeda Galaxy, like M13, the globular cluster. And again, they do a great job with Orion, the Pleiades. There's a lot of cool stuff that binoculars work really well with.
Yeah, and I'd say especially if you've got a good dark sky, there's so much that you can see, and you've got such a wide field that you can really see a lot of the structure, especially in the band of the Milky Way, that a good telescope is not going to be able to show you because it's looking at such a tiny part of the sky. And just to piggyback onto Theo's recommendation of the Dobsonian telescope, that's the kind that we typically recommend. We recommend the simple ones that don't have any of the fancy, little computer pads or the motors that move it, because, well, first of all, that adds to your price. But second, personally having used them for many years and really starting out in astronomy with the Dobsonian, they teach you the night sky, because to find something, you have to get the telescope pointed at it. It's not going to move for you. And that really, for me, it gave me much more of an appreciation of the night sky. And I had much more satisfaction when I actually found the object I was looking for versus something just zipping over to it. Not saying that the robotic telescopes aren't cool and aren't warranted, But especially if you're beginning, that's really the way to do it. And you learn the night sky so well. And then you're able to talk more about, what's up there, especially if you're showing kids or grandkids or friends.
Yep.
So.
Yeah, just to echo that, I own 6, soon to be 7 telescopes. And my 10-inch Dobsoni is the one that gets used the most. And it's quick and dirty. I mean, you can set it up in about a minute and you're rolling. And I mean, the views are spectacular. So fits right in the back of my mini SUV, very easy to transport. So I'm a big fan of either an 8-inch or a 10-inch Dobsoni. And also, you mentioned donations. I had a guy reach out to me just this week, had a telescope, not using it anymore. It's in his attic. I think it's a 6-inch. I need to get over there and pick it up. But of course, I'm running out of attic space now. So there's always people within your local astronomical society who probably have a telescope that they're looking to part ways with. Ask me how I know. So that would be a great place to start. Reach out to your local astronomical society, see if there are either telescope loaner programs or someone who's looking to donate a telescope. And you would probably be doing them a favor, possibly saving their marriage by taking it off their hands.
Jeremy, it's just, it's really bad when both of you are in that hobby,
Oh, man.
I was just going to say, if you don't have a local astronomical society in your area, maybe check with the local university, because that's typically a place where people will contact if they want to donate. You could always just leave your name and number and say, if somebody ever calls and wants to donate something, just give them my number, because a lot of times the university may not necessarily have a need for the equipment and don't want to take it if it's not going to be used. All right, anybody else? I think, let's see here. Yes, we got a comment here. I use binoculars just as much as my telescope. So star hopping with binoculars is fun. I definitely would agree with that. Looks like that might be the last question out of our chat, and we're actually over by a few minutes. Not too bad, but if you have any other questions, just pop them in the chat and we'll try to get to them. But before we wrap up here, and but in the meantime, I think we'll go ahead and call it a night. I'd like to thank all of our presenters from the Barnard Seaford Astronomical Society, the Memphis Astronomical Society, Bays Mountain Park and Planetarium, McGill Space Institute, and University of Illinois at Springfield. And we're hoping to do this next month as well. So just keep an eye out, maybe on the Dyer website, on our social media. And we will try to advertise that at least a couple of weeks beforehand. And hopefully we will have some good clear skies so that a lot of us can be out at telescopes and showing some of the things that are above you right now that you can appreciate. So with that, I don't see any other questions. So, and again, thanks to Brian Smokler for making sure our stream is going out to everybody, and for my colleagues at Dyer that are helping behind the scenes there. So hope everyone has a good weekend and stay warm.